Our next talk will be by Scott Aaronson, titled Shadow Tomography of Quantum States, Progress and Prospects. Scott, we need to pass the button to you. Yeah, you have, yeah. The floor is yours.
Can you hear me?
Yes, we can.
All right, great. All right, I'm going to try sharing. Can you see that?
We can see.
Good. All right. Well, thank you very much for inviting me. And you know, in Charlie and Ike, I have a difficult act to follow, but I'm grateful actually that Charlie covered so many of the basics of quantum information, so now I can just assume that everyone knows them and proceed. This talk, I guess, in fitting with the theme of the informational lens, is going to be about an information theoretic question about quantum states that for some reason no one really thought to ask before a few years ago. But by now we've actually learned a lot about it, and we're starting to find some applications of it. Okay, so this is a task that I call shadow tomography of quantum states. Actually, it was a physicist, Steve Lamia, who suggested this name to me. I have found that physicists are just consistently better at naming things than computer scientists are. Okay, but let me sort of set the stage for this. So, you know, as you heard in Charlie's talk, you know, a central feature of quantum mechanics is that measurements are inherently destructive operations. So you know, if we consider just a single qubit, like alpha 0 plus beta 1, then you know, in some sense, a qubit already takes infinitely many classical bits to specify, right? Because alpha and beta can be complex numbers, and there's a whole continuum of them. Okay, but as soon as we look at the qubit to ask it what it is, then it returns only a single bit of information. If we ask it whether it's 0 or 1, then it just picks one randomly with the appropriate probabilities, and it snaps to whichever one it picked. So, you know, it just pretends that it never was anything other than 1. Okay, so what this means is that, you know, a measurement actually changed the state, it damaged it. Now all of the information about the amplitudes, alpha and beta, is gone, except whatever could be inferred from the fact that we saw one outcome. Okay, so now this destructiveness of measurement is exactly what opens up so many of the cryptographic possibilities of quantum information, including Wiesner's quantum money, including quantum key distribution, both of which Charlie told you about. But it can also be a huge practical limitation. So, like if you're trying to learn something about a state, well, you know, you only get this one chance to measure it. You get this tiny little signal from the measurement, and then the rest of the state is gone, right? So how do we deal with that if we're trying to, you know, learn about the states that would arise in the lab? Okay, and you know, as we know, another central feature of quantum mechanics is that there is a lot there to be destroyed. If we considered a quantum state of, let's say, n quantum bits, n qubits, then to specify such a state, we need a list of 2 to the n complex numbers, okay, 2 to the n power amplitudes, one for every possible configuration of all n of the bits. Okay, so there is sort of an exponential amount of information that's at least implicitly there in a description of the quantum state. And yet, when we look, of course, we only see n bits. Okay, we collapse and we just see a single outcome for each of the qubits. And these alpha sub x's, these amplitudes, only arise in determining the probabilities that we're going to see one outcome versus another one. Okay, furthermore, a fundamental result proved in the 1970s, Halevo's theorem, tells us that in some sense there is no clever way around that. Okay, so if you had n bits that you wanted to communicate to somebody by sending them qubits across a channel, and if that person has to be able to learn your bits reliably, then you actually need to send them n qubits. There is no compression possible because of the limitations that come from measurement. You can get a small improvement to n over 2 qubits if you share prior entanglement with the recipient, as Charlie also mentioned. Okay, so this raises a philosophical question. Should you say that these amplitudes, these 2 to the n complex numbers, are really there in the quantum state? Or sort of that they're really there in nature, in the universe, or are they just part of our description of the universe? Are they like a mental bookkeeping device? Notice that if we were talking about a probability distribution over n-bit strings, then we might be tempted to say, well, there aren't really 2 to the n parameters, right? There's just a single string of n bits, and it's simply that we don't know which string it is, and therefore we represent our ignorance of that string using a probability distribution, which is a list of 2 to the n real numbers. Okay, but in the quantum case, it's a little bit harder to stuff this 2 to the n sized vector entirely into our heads, because, of course, the amplitudes can interfere with each other, right? Which is a physical effect that tells us that, in some sense, all of the components of our quantum superposition had a physical effect. Okay, so the people have argued about these sorts of questions for almost a century. There are epistemic and ontic views of quantum states. I'm not going to get into that. What the tack that I'm going to take in this talk is to sort of investigate the question from a more practical information theoretic standpoint. What does a quantum state act like when we are trying to characterize it, when we're trying to learn about it, when we're trying to learn about its behavior with respect to various measurements or observables? Okay, so this brings us to one of the central tasks, or problems that you might have about a quantum state. Okay, and this is the problem of quantum state tomography, which has been central in experimental quantum physics for many decades. Okay, and the task is very simple. We have lots and lots of copies of some quantum state. Let's say that it's a d-dimensional state, so it could be a superposition over d different things. But more generally than a superposition, it could even be a mixture of different superpositions, a probabilistic mixture, or what we call a mixed state. Right, a mixed state is the most general kind of state that's allowed in quantum mechanics, and every d-dimensional mixed state can be specified by a d by d matrix, which is a Hermitian matrix, positive semi-definite, and its trace is equal to 1. Right? That's what a mixed state means. Any mixed state can be thought of as just a probability distribution over different quantum superposition states, which in this context we call pure states. The subtlety is that the same mixed state could be represented as different probability distributions over pure states. Okay, so it can be written as a distribution over pure states in general in infinitely many different ways. Okay, but that's a mixed state, and so a general situation that experimentalists would have is that they have a machine, let's say, every time they turn their machine on, it generates some quantum state, rho, say some mixed state, and now they would like to know what rho is. Of course, they don't have to know exactly, but at least they'd like to know the entries of this d by d matrix to some reasonable precision, okay, so that they can publish their Nature paper and show that they got the quantum state that they were expecting. Okay, So now, a very basic question we could ask is how many copies of rho are necessary and sufficient to do quantum state tomography? Okay, well, a D by D matrix has on the order of D squared independent parameters in it. So, you might guess that the answer should be, well, something like D squared copies, right? And, the problem being that each copy, again, we only get to measure it once, and we get just a little tiny bit of information out. Okay, well, in fact, that does turn out to be the right answer. About D squared copies of rho are necessary and sufficient. However, that was astonishingly hard to prove. It was only proven actually a few years ago in independent works, one of them by O'Donnell and Wright, and the other one by Zheng Ha et al. The upper bound is particularly hard. It was, it had been shown that D cubed copies suffice, but to get down to D squared, you actually needed a lot of representation theory. It's not quite as hard to show that D squared copies are information theoretically necessary. Okay, but in any case, this is a D squared is a problem for any quantum states of reasonable size, such as we're going to have, let's say, on in the coming generation of NISQ quantum computers with 50 qubits, with 60 qubits, with 100 qubits. How big is D going to be? Well, remember, D is 2 to the n, where n is the number of qubits, right? Which means that D squared is 4 to the n. Okay, so what we're saying is to characterize your quantum state, you need a number of experiments that grows like 4 to the power of the number of qubits. Okay, that that can just barely be done for 10 qubits. It was done a few years ago, by a heroic effort that required millions of measurement settings. I don't know how many hours of grad student time where we're involved with that. Okay, and this is clearly not going to scale. I mean, to even 20 or 30 qubits, let alone 50 or 100. In fact, you won't even have enough information. You won't even have enough room to write down a full description of the quantum state. Beyond 60 or 70 qubits. You'll have to use you'll fill up all the hard disk space of a supercomputer like Summit, very, very quickly. Okay, so this motivates the search for new ideas. Is there something that could serve like quantum state tomography, but without requiring this many copies of our state? Okay, so for various reasons, around 2016, I defined a problem that I call for which I adopted the name of shadow tomography. I didn't know whether this was possible or not, but I raised the question. Okay, and let me tell you what this task is. So we're given an unknown quantum state, so like a d-dimensional quantum mixed state, call it rho. And we're also given, we have a list of just, let's say, 2 outcome measurements, E1 up to EM. Okay, and I'll assume that the measurements are known to us. Okay, so we know which measurements we care about. And now what we want is for each of those measurements, for each EI, we want to estimate the probability that EI accepts rho. Or as a physicist would call it, we want the expectation value of that measurement operator. Okay, we want so in other words, we don't need to know rho entirely as a D by D matrix, right? We've given up on that because that just requires too many parameters. Okay, instead, we will settle for knowing how rho behaves with respect to these M measurements. Or if you like, we want to know the shadow that rho casts on these M measurements each of which, has only two outcomes, could either accept rho or reject it. Now let's think about this problem. How many copies of rho are needed if this is what you want? Well, we can observe right off the bat that if we had enough copies of rho to do full quantum state tomography, well, then of course we could also do shadow tomography, right? Once you know rho as a D by D matrix, then you can estimate the probability that any measurement accepts it, right? So therefore, D squared copies of rho are going to suffice. But now at a completely different extreme of parameters, we see that about m copies of rho would also suffice. A number that would scale like the number of measurements that we care about. Why? Because if we've got m copies, then we can just apply each measurement, each EI, to some separate copies of rho, and then just estimate, the expectation value of each EI separately from the other ones. Okay, so we have two trivial upper bounds, but is either of them a lower bound? So the question that I raised was, well, what if D and M are both exponentially large? As could very easily happen, right? We could be dealing with a state of n qubits, so that D is like 2 to the n power. And maybe we care about, a very, very long list of measurements. For example, all accept or reject measurements that could be described using small quantum circuits, that could be implemented using a small number of 2 qubit gates. Okay, so in that case, D and M are both exponential, but we might ask, could we still achieve this task of shadow tomography using a polynomial in the number of qubits, number of copies of rho? Okay, or another way to ask it is, could we do this with a number of copies of rho that grows polynomially only with log D and log M? Okay, now my guess was that this wasn't possible. I tried to rule it out, but I found that, this wouldn't conflict with Halevo's theorem. It wouldn't conflict with any of the principles of quantum information theory that I knew. I just couldn't rule it out. And eventually I understood why I had failed to rule it out. And the reason was that it is possible. Okay, so a couple of years ago, I gave the first protocol for shadow tomography, at least an information theoretic protocol, and it uses about the number of copies that is shown here. So I need a number of copies of rho, like log of D. Okay, so like the log of the Hilbert space dimension. And it also scales like log of m to the 4th power, where again, m is the number of 2 outcome measurements that we care about. And it scales like 1 over epsilon to the 4th, where epsilon is the additive error in each of our probability estimates. Okay, to what extent this can be improved is a question that we'll come to later. For now, I want to say a little bit about how does this protocol work. Oh, well, actually, even before that, I want to say a little bit about what are its implications. Okay, so maybe the main implication is that if we are given an n qubit quantum state psi, let's say for simplicity now that it's a pure state, then for any fixed polynomial p, by measuring only a polynomial in n number of copies of psi, we can learn the behavior of psi on every quantum circuit with at most p of n gates. Or by behavior, I mean the approximate probability that that circuit accepts psi or rejects psi. Okay, so this, is kind of surprising, right? The quantum state is this exponentially large object. We have, an exponential number of different, small circuits with respect to which we might want to know the state's behavior. And yet a polynomial number of copies of the state suffices for us to get that information. Okay, now to be clear, I don't say that this will be computationally efficient. Okay, we're going to have to measure our polynomial number of copies of psi in a very, very careful way to avoid destroying them, in the process of learning about them. And our measurement procedure will take exponential time. And there are some reasons to think that should be unavoidable. That should just be inherent to the task that we're trying to do, although we don't know that for sure. Okay, so now another implication. Here is an implication for the future quantum software industry. Okay, that if in the future, let's say we had people who were selling quantum states that you could just plug into your quantum computer and use as software. That is, like, use them as a program. That could be run on many different inputs, and each input giving you a different way to measure the state in order to maybe learn the value of some function. Well, you might if you're the software company, you might hope that you could sell like one-time programs, or programs that people would only be able to evaluate on one input or on a few inputs. And after that, the program would just disappear, and the customer would have to go back to the software company and buy a new one. Okay, but what the shadow tomography theorem implies is that in some sense that is not possible. Not it's even just at least in an information theoretic sense, given any quantum program rho with a polynomial number of qubits. If you have a polynomial number of copies of that program, then that is enough, at least information theoretically, to approximate the acceptance probability of that program on every n-bit input. Okay, so to see, what is the chance that it accepts or that it rejects on every n-bit input, regardless of the program. Okay, which means that any scheme for copy protecting quantum software, to whatever extent that is possible at all, it will have to rely on computational assumptions. It cannot just be information theoretic. We get a similar implication about quantum money. So since the groundbreaking scheme of Wiesner that Charlie Bennett told you about, there's been a lot of research toward improving Wiesner's money scheme. And one way you could hope to improve it, actually Charlie himself was involved with in the early 80s, you can use a pseudo-random function held by the bank in order to decrease the amount of secret information that the bank has. So instead of needing a gigantic number of secrets, like a different one for every bill in circulation, the bank might need only a single secret. But then the drawback is that the security of your scheme depends on your belief in the pseudo-randomness of the bank's pseudo-random function, right? That it uses to sort of expand its small secret on the fly. So some years ago, I raised the question, could there be a quantum money scheme where one has information theoretic security, just like with Wiesner's original scheme, but where the bank only needs to remember a small secret, as in the scheme of Bennett et al. From the early 80s. The quantum tomography theorem implies that the answer to that question is no. Okay? Every quantum money scheme requires either computational assumptions or else a giant secret on the part of the bank. And the reason is, again, that if we have only a small secret, then a counterfeiter with unlimited time could take a polynomial number of legitimate money bills and do shadow tomography on them to sort of try every possible key and figure out how to counterfeit the money. Okay, now I would love to know if there are experimental applications of shadow tomography, and we'll come back to that toward the end. But making this more practical toward possible experimental realizations. All right, so now, to design a scheme for something like shadow tomography, a key primitive that we need is what's called gentle measurement, which has been, versions of which have been discovered, many times in the quantum information literature. Okay, but the basic idea here is that suppose that we make a measurement on a quantum state rho, and suppose that this measurement has an almost guaranteed outcome on this state. Okay, so like this measurement accepts rho with probability at least 1 minus epsilon. Okay, then it turns out that such a measurement on such a state does not damage the state by very much. Okay, so after the measurement, we can recover a state, call it rho prime, that is close to our original state rho. Its trace distance, which is our usual distance metric on quantum states, from rho is at most the square root of epsilon. Okay, so intuitively, like if I took a state that was very nearly zero and I measured it in the 0-1 basis, almost all of the time it's just going to snap to zero, right? Which is a very small change to that state. Okay, so while it's true that every measurement has a potential to damage the state that's being measured, that potential is sort of only happens when we measure in the wrong basis, as it were. When we measure in a basis that does not have any basis elements that are close to the state that we're measuring. Okay, so now this is a very important principle, and it has a generalization. Which says that we can actually apply many such measurements in succession to a state rho, let's say m of them, and they will all accept with a high probability, as long as epsilon is tiny compared to 1 over m. Okay, and the total damage to the state will also be very small. It will be at most like m times the square root of epsilon. Okay, and this is intuitively because of the linearity of quantum mechanics. We can sort of just decompose and think about each measurement separately. Now, this technique of gentle measurement is often combined with amplification, which would mean that instead of measuring just one copy of my state rho, to see does this measurement accept rho or reject it, I will take k copies of rho. Okay, and now I will implement a single measurement that does the following, that says simulate applying my measurement to each of these k copies, and then only tell me, did the majority of the measurements accept or did the majority of them reject? Okay, so this is called an amplified measurement, and we use this for the same reason why it's used all over theoretical computer science, namely that this pushes down the probability of an error at an exponential rate, just because of this, for this usual Chernoff bound reasons, for the usual concentration of measure reasons. Now the damage to our state, like our epsilon, becomes like 1 over exponential in the number of copies of the state. Okay, so gentle measurement and amplification are so wonderful. You might ask yourself, well, then why don't they just immediately solve the shadow tomography problem? Why can't we just use those and just do an amplified gentle measurement for each of our measurements, E1, E2, up to EM, until we're done? Well, let me tell you what the problem is. Okay, if we try that, then we will be able to prove a shadow tomography theorem, but only for a promise gap version of the problem. Meaning if we have our M measurements that we care about, say E1 up to EM, and let's say we have some real numbers, C1 up to CM. Now let's say that someone promised us that for each I, the probability that the ith measurement, EI, accepts our state rho is either at least CI or else at most CI minus epsilon. Okay, so we had a gap for each measurement. Okay, then, just using gentle measurement on a relatively small number of copies of rho, we could easily figure out which side of the boundary we're on for each eye. Okay, and each time we're not going to damage the state by very much. Okay, but the procedure really depended on that promised gap. Okay, and now if there's no promise like that, then you can never rule out a priori that one of your measurements, one or more of your measurements, EI, might be right on the knife edge between what you want to count as like a yes outcome and what you want to count as a no outcome. Okay, and if that's the situation, if you're right on a knife edge like that, then it's not, the problem is not merely that you're going to fail to get a good estimate of the probability that EI accepts rho. The problem is worse than that. It's that when you try to make the measurement, you will destroy your copies of rho, okay, because the amplification will fail. And you can afford to destroy a few copies of rho, right? But the total number of copies that we want to use is only polylogarithmic in M and in D, right? In the Hilbert space dimension and in the number of measurements. So we really can't afford to destroy copies of rho every time we try to measure. We have to be much more careful. Okay, so our contribution was to solve this problem basically. So the proof really involved putting together a few previous ingredients in quantum information. Now, a first ingredient was something that I called the post-selected learning theorem. Okay, so way back in 2004, when I was a grad student, actually I believe I was visiting IBM, Yorktown Heights, when I proved this theorem. Okay, but I was interested in a scenario where Alice has a quantum state rho, which she is trying to describe to Bob, let's say with respect to its behavior on M different measurements, E1 up to EM. So let's say that Alice knows what the state is. Okay, Bob does not know what it is. But Bob just wants to learn whether what each of these measurements do on rho. Like, what is approximately the chance that each one accepts rho? Okay, well, of course, Alice could just tell Bob that, but that would take like M bits, or she could tell Bob a description of rho that would take like D squared bits. But here is something she can do that is more efficient than either of this. She can say to Bob, "Listen, Bob, I want you to just imagine that rho is the maximally mixed state, or in other words, a completely uniformly random string. So just start by assuming that you know nothing about rho, as indeed he doesn't. Okay, or actually he'll imagine an amplified version of rho. Okay, and then what Alice is going to do is she's going to repeatedly correct his guess in a sort of Darwinian fashion. Okay, so she's going to repeatedly communicate to Bob, say to him, here is a measurement, EI, on which your current guess, your current hypothesis state will give you a badly wrong answer. And here is what the right answer should be on that measurement, EI. Okay, then Bob, after getting that information, can improve his guess by letting his state be whatever state you would get by starting from his previous hypothesis and then post-selecting on getting the answer that Alice just told him that he would get on EI. Okay, he can do this at least as a mental experiment, right? He can say, what would happen if I conditioned on getting the right answer? And does this again and again. Now, any of you who know machine learning might be reminded, this sounds kind of like boosting. It sounds kind of like what's called the multiplicative weights update method. This is very related to all of those things. Okay, and What we prove is that this has to converge after a number of iterations that goes only like the log of the Hilbert space dimension, maybe not to rho itself, but at any rate to some state that behaves like rho with respect to each of the m measurements, E1 up to En. Okay, and that was all that we needed. So that was the key point. Okay, so at the time I used this result mostly for quantum complexity theory. I used it to show that BQP, or quantum polynomial time with quantum advice, can be simulated by, in a classical complexity class, PP, like sort of like a counting complexity class with classical advice. You can always replace quantum advice by classical advice as long as you have exponentially more time to sort of interpret what the classical advice is trying to tell you, which, you know, in this case would mean simulating that post-selection procedure. Okay, so now how can we use this to get shadow tomography? Well, this procedure by itself does not get us all the way there, and the reason is that you know, Bob relied on Alice telling him like which measurement would be a good one to condition on next, right? So he relied on an all-knowing advisor who actually knew a description of the quantum state rho that we were dealing with. Okay, but of course, in the real shadow tomography problem, we don't have that. We just have a bunch of copies of rho in our lab. And you know, so if we want to find measurements that are informative about rho, then we've got to find them ourselves. So we need a second result, which I call the quantum or bound. This was something that I claimed to prove in 2006. Then a few years ago, Aram Harrow, Cedric Lin, and Ashley Montanaro discovered a bug in my proof. My protocol might or might not be sound. That remains an open problem. But very helpfully, they also designed a different protocol for which they could prove soundness. Okay, so now this is a theorem after all. What the quantum or bound says is that, well, let's say that we've got an unknown mixed state, rho, and let's say that once again, we've got some known two outcome measurements, E1 up to En. Okay, now suppose we're promised that one of two things is true. Either there is some measurement I in our list, some EI, that accepts rho with a high probability at least C, let's say, or else every EI in our list accepts rho with probability at most C minus epsilon. Okay, then we can decide which with a high probability given only a few copies of rho, about log m over epsilon squared copies. It actually, surprisingly, does not depend on the Hilbert space dimension at all. Okay, and then you know, once this has been proved, we know a few different ways to prove this now. One is using what's called Mariotte-Watrous amplification. Another is, you know, using like a very clever custom test that Harrow, Lin, and Montanaro designed. But once you have it, you can then leverage it further to get a protocol that uses now about log to the fourth m copies of rho. So it's less efficient, but you know, still polynomial in log m, and that will actually find the I. Okay, they'll actually find the measurement in your list that accepts rho with a high probability, provided that there is such a measurement. Okay, so then how much time do I have?
That's a tricky question because we started later, right?
We did start later, yes.
Yeah,
I think yeah.
Yeah, probably you know, for 5 more minutes, just to be fair with you know, starting later.
All right. I'll try for 5 minutes. All right. So
thank you.
Yeah, sure. So so once you have that, then by putting these two things together, we can get a shadow tomography procedure where the way it works is we sort of repeatedly do a search among all M of our measurements for one that will be informative, meaning that disagrees with our current hypothesis by a lot on the state rho. And then once we find that, then we use it to improve our hypothesis. And then, we use this theorem that after only about order, log of D repetitions, we have to end up with something that behaves like rho with respect to our M measurements. Okay, so, of course, the question still stands. Well, what is the true sample complexity of shadow tomography? I gave this upper bound here, but in the other direction, the only lower bound that I know is a fairly trivial one. I know that you need at least log M over epsilon squared measurements. I don't even know that copies of rho, rather. I don't even know that the number of copies of rho needs to have any dependence on D. Okay, so can the upper bound be improved? So this brings me to a more recent result, which I'll only sort of have, be able to give you a vague impression of. I don't have time to go into details, but in a more recent paper by me and Guy Rothblum, we were able to improve the dependence on log of M, give a new shadow tomography procedure, which had some additional advantages. The new procedure is fully online, meaning you can just tell the procedure one at a time what measurements you care about. Like E1, it tells you what's the probability that E1 accepts rho. You tell it E2, it tells you the probability that E2 accepts rho, and so forth. Okay, it computes each answer on the fly. And also, this procedure is gentle. After it's done, your copies of rho will be damaged only slightly, and you can reuse them for something else. Now, the way that we achieved all that was as byproducts of a new connection that we made between the problem of gentle measurement of quantum states and what might seem like a totally unrelated topic in theoretical computer science, and that is the field of differential privacy. Okay, and that connection is a story in itself. So, in the few minutes that I have, I'll just say a tiny bit about it. So first of all, by a measurement being gentle on a set of states, like let's say we've got a measurement M, I call it alpha gentle on a set of states S if for every state rho in that set, and for every possible outcome Y of the measurement, the post-measurement state, like if the outcome is Y, so the state that's left over, if I condition on the outcome Y, has a trace distance at most alpha from my original state rho. Okay, and we are typically interested in measurements that are gentle on the set of product states. Okay, so just tensor products, let's say, of n different states. Okay, now what might seem a completely different topic, what do I mean by a measurement being gentle? Well, if we have n, let's say, unentangled qubits, if I measure the Hamming weight, like the total number of ones, that could be an extremely destructive operation, right? Because intuitively, I've got this wave packet, I've got this superposition over many different Hamming weights that will, typically follow a Gaussian. But then if I measure to learn the exact Hamming weight, well, then I have localized that wave packet, to a single Hamming weight. But the physicists have known for a long time that there is a safer thing I can do that still tells me a lot about the Hamming weight, and that is to sort of deliberately add noise to my measurement outcome before I measure. So I can say, I want to make a measurement that only tells me the Hamming weight plus some, for example, Laplacian noise that I've deliberately added. Now, the advantage of that is that if the noise is large compared to the standard deviation of my wave packet, then by making the measurement, I don't learn sort of which component of the superposition I was in, or I don't learn much about that. And for that reason, I don't damage the superposition by very much. Okay, so this is a beautiful technique. Now, what on earth would it have to do with differential privacy? So, differential privacy is sort of like theoretical computer science applied to the social world, about as far as you could get from the subatomic world, right? But it's a notion that was defined by Cynthia Dwork and her collaborators about 15 years ago. And it's a condition on algorithms that could query databases. That says that it's a sort of a multiplicative closeness guarantee. It says if I change only one entry of my database, like let's say I've got a database of medical records, and I change whether one person has cancer or doesn't have cancer, then that should produce only a small change to the probability of any possible output of my algorithm. Okay, and once again, a typical way that we achieve differential privacy is by deliberately adding noise to the results of our queries before we return them. Okay, this was what sort of tipped us off that there might be some connection between the two. Now, one can define a quantum version of differential privacy. If one wants to protect the privacy rights of electrons, this is just the quantum version of what I said before. And and the same measurements that achieve gentleness, or in practice, we notice we're often the ones that achieve this differential privacy. So what we did is we proved a theorem that explains this pattern. We proved a two-way connection. We can prove that, first of all, any measurement that is alpha gentle on product states for small alpha is also O of alpha differentially private on product states. And secondly, any measurement that's epsilon differentially private on product states and that satisfies some technical conditions that I won't go into, most of the measurements we care about do satisfy it, is also O of epsilon times square root of n gentle on product states. This square root of n factor we can show is actually tight. The restriction to product states is also necessary to get an interesting theorem here. This part we don't know if it's necessary. Okay, but bottom line, as a sort of a flagship application of this new connection between quantum measurement and differential privacy, Guy and I were able to prove a new shadow tomography theorem that says that you can use this number of samples. So here, notice that it goes only like log of m squared. The dependence on d and on 1 over epsilon are a little worse than before, but the dependence on m is better, at least. And furthermore, our new procedure, as I said, is also online and gentle. And the way that we did this was, fundamentally by taking known work from the classical differential privacy literature, something called the private multiplicative weights algorithm of Hart and Rothblum, and quantizing it. Okay, we gave a quantum version of that procedure, and we used our connection theorem to analyze it and show that because it was differentially private, therefore it was also gentle and it was not damaging our states by too much. Okay, so one can ask about the computational complexity of shadow tomography. There are interesting questions there, but because I'm running out of time, I'm just going to end with this slide. Can we make shadow tomography practical? I want to just call your attention to, there was a beautiful work just this year by Huang, Kueng, and John Preskill that built on the idea of shadow tomography, but that actually gave some procedures that are a lot closer to experimental realization. Like they don't require sort of carefully maintaining a quantum state from one measurement to the next to the next. You can just measure everything in one shot. For example, they can estimate the fidelity between your unknown quantum state rho and a list of exponentially many different pure states, which is fixed in advance, given only a polynomial number of copies of the state rho. Okay, and this has some neat applications, including one that my student, William Kretschmer, just thought of. But to make things truly practical, we would like, first of all, to get better sample complexity. Secondly, to get better computational complexity. And thirdly, to get all these wonderful benefits that we get from shadow tomography, but with measurements that are easier to implement experimentally. All three of those remain wonderful open problems. So let me stop now. Thank you for listening.
Thank you very much, Scott, for showing us, getting us out of the shadows.